Hey there, hi there, who there? Welcome to Unit 6, igneous rocks and volcanoes. Good stuff. Gonna be hot. Alright, so we spent kind of the first portion of the semester talking about the tectonic cycle, and now we're going to talk about that tectonic cycle influence on the rock cycle. So because of the layers of the earth, because of plates moving around, that does affect the rock cycle. Specifically, it intersects the rock cycle as we're talking about igneous rocks. We're talking about magma, lava, volcanoes, igneous rocks. So we're going to be in this realm of the rock cycle. And in last unit, we did touch real quick, I think this image was actually there too, on igneous rocks, kind of what they look like. We'll do so again, spend a little bit more time in detail talking about igneous rocks, how they form. But some indications of igneous rocks would be, some good, strong crystal matrix. That's a bunch of crystals stuck together. Igneous rocks sometimes are vesicular. They have holes in them. So, really cool rocks, even though they formed from a hot process. Hey-o! All right, so let's talk about, where they come from. So we got to start off talking about molten rock. All right, there's two types of molten rock, even though it's the same exact stuff. You have magma, which is molten rock, liquid hot rock, below Earth's surface. And as that magma kind of makes its way towards the surface, up, and as soon as it gets close to or near the surface, it's called lava. Molten rock above Earth's surface. It's two different names for the same stuff. Why, I don't know. So, where does molten or liquid hot magma come from? So magma, lava, is a liquid. So where might this liquid come from? This liquid hot rock. Where would a liquid hot rock come from? Trick question. It's not the outer core. Not even close. Well, where the magma does come from is somewhere between the crust and the mantle, really way up here. So the outer core liquid, that's way too far away. The heat from the outer core is transferred to the mostly solid mantle, and the mantle convection driving the plate tectonic cycle on Earth. But it's the interaction between the crust and the mantle. So just a thin little area between the crust and the mantle, that's where liquid hot magma forms. All right. So again, looking just where the crust and where the mantle kind of intersect, and typically where there's some sort of boundary, not always, but typically where there's some sort of boundary, convergent boundaries, divergent boundaries. However, every once in a while you can get a magma zone kind of in the middle of nowhere underneath the crust, whether it's continental crust or oceanic crust, nowhere near a boundary, and those are special little hot spots. So, how do we get that magma? If the crust is solid and the magma is mostly solid, how do we get this liquid magma stuff? Well, magma forms from the partial melting of upper mantle material and the crust, so that kind of intersection between the mantle and the crust. As mantle material kind of moves upward due to mantle convection, or has water added to it, when there's a subduction zone, as that plate is being driven below, it brings stuff with it, including water. So as mantle material is moving upward due to convection, or water is being added to it, it starts to melt a little bit. As that mantle material rises, gas bubbles in the magma comes out of solution and form bubbles, and as the bubbles rise, they expand. This is due to less pressure as you get closer and closer to the surface. Eventually, the pressure from these bubbles is stronger than the surrounding rock, and the surrounding rock fractures, allowing the magma to get to the surface. All right, so it's already kind of welling up. Mantle convection is helping the process, possibly. Water added to mantle material is melting it, and it's less dense, so it's already kind of making its way up. But all the gas bubbles trapped in there facilitate and help this process. So there's two main methods in which mantle crust interaction that area melts. The first method is a reduction in pressure, a dry melt. This usually happens when mantle material pushes upward into the areas formerly occupied to the crust due to either crustal thinning, like what we saw in one of those demonstration videos when we were talking about plate tectonics and the basin range formation in Arizona, where there's cracks in the crust or divergent boundaries. As plates move apart, that mantle material makes its way upwards, filling in that gap. The pressure drops the closer you get to Earth's surface. Therefore, the melting temperature of minerals also drops. So, deep below ground, a mineral might need to hit a temperature of, I'm just making up numbers now, 2,500 degrees to melt. But because of the reduction in pressure, the further you get to the surface, well, the minerals might only need 500 degrees to melt. So you get a dropping in melting temperature, making solid material more easy to melt. An example is if you boil water at sea level where the air pressure is higher, it boils at 212 degrees Fahrenheit. But you go to the top of a mountain and boil that same water, it boils at only 200 degrees Fahrenheit because there's less pressure. Less pressure means, less temperature for the material to go from solid to liquid, or in this example, liquid to a gas when you're boiling. So either a reduction in pressure, again, oftentimes due to mantle convection, typical around divergent boundaries or crustal thinning, or you get a wet melt called flux melting. H2O, water, and carbon dioxide, CO2, is dragged into the mantle at subduction zones. So now we're talking about convergent boundaries. All right. Both of these material, water and carbon dioxide, move through the crystal mush of a mantle body, magma body, and it chemically lowers silica's melting point by several hundred degrees. Silica, SiO2, quartz. So you're adding like some material to this chemical concoction to lower the melting point of a typical mineral. So you're lowering the melting point, making it easier for that material to melt, turn to liquid magma. Once a wet melt has started, the pockets of liquid magma start to incorporate more and more silica from the surrounding rock. So as you create this liquid hot magma, and it's less dense than the surrounding mantle and crust, so it's starting to make its way up. It's starting to melt the material around it, creating more and more and more and more magma, but creating a more stickier magma, something that is less runny, so it's more sticky as it kind of continues to melt the surrounding silica out of the rock as it's bubbling through it, or it's making its way through it. So, what's the deal here? So what's with all that? Okay, so it can get kind of complicated because where magma originates from determines what it will do. It will determine the type of volcano that's created. It will determine the type of igneous rocks that are created. So it has a whole heck of a lot to do with the rock cycle. So from what I just talked about, which kind of sounds maybe a little complicated, just take away that the mantle material, the interaction between the crust and the mantles, the area around kind of the upper mantle material, it will melt either due to like a reduction in pressure, like a divergent boundaries or crustal thinning, or will melt due to the addition of material, wet melting, water, and carbon dioxide. Either or is going to help that mantle material melt to liquid. Liquid is less dense than the surrounding rock, so it will begin to rise. Just let that sink in a little bit. We'll pause here. All right, we pause here. I don't want to give you too much information. Let your brain take a little break. We'll pause here. When we'll come back, we'll talk about the three different kinds of magma that are created. Because again, where that magma originates, what material is being melted, that will all determine the type of magma, which will determine the type of possibly volcanic activity, which will determine the type of igneous rock. So we'll pause here just for this in this first section, and I'll see you back here in just a minute.